Hello and welcome to Crazy Math Productions. Today we're looking at simplifying radicals. In our unit here we're going to be looking at quadratic equations, radical expressions. So yesterday, or the previous lesson, we were looking at the system of just simplifying things in general. We're going to simplify the radical expressions a little more specifically with three rules today. We have no radicands that have perfect square factors. Of course, when does not count. No radicands containing fractions, and no radicals in the denominator. So let's see what that looks like. We're going to be using two tools today. First of all, you can break apart if you have multiplication. If you have a product, you can break that radical apart. Remember, the radicand is, for example, b, that is in the radicand. The radical is the actual symbol. And we can also break it apart by the quotient, by the division. So we can break it apart in the top and the bottom. So let's go ahead and use this. Now we're going to have more examples here than we really need, so please feel to fast forward or just pause and see if you can do these on your own as we go. Now there's going to be two different distinct methods that we can use for each one of these. We have the breakdown of prime numbers, or we can look for perfect primes, perfect squares in the as factors. All right, so let's go ahead and do both. 18, 2 divides into it 9 times, and that's 3 and 3. So this will be the square root of 2 times 3 times 3. Now you notice that there are two 3's. Basically, for every 2 you see, pull 1 outside. So it's 3 square roots of 2. The other method is just to simply look. We have 4, of course, is 2 times 2, 3 times 3, 9, 4 times 4, 16, 5 times 5, 25, 6 times 6, 36, and so on. These are our perfect squares. And as we go through, we want to see what of these will divide into 18 easily. What will be a factor of 18? So 18 divided by 4, that's not going to work. It's going to be 4.5. 18 divided by 9 is 2. That works nicely. So we're going to say, well, that's 9 times 2. Well, the square root of 9, I can break apart from the square root of 2, and we get 3 square roots of 2, because square root of 9 is 3. So again, you can do it either way, and I'm going to do it both ways for a little while here. Now, square root of 72, we can break that down into 2 and 36. 36 is 2 and 18. 2 and 9, 3 and 3. So we have the square root of, that's quite a list, 2 times 2 times 2 times 3 times 3. We see 2 2's, pull that out. We see 2 3's, pull one of those out. And we're left with a 2 that's inside. Now 2 times 3 is 6 times the square root of 2. And that is as simplified as it gets. Now, 72, we notice 4 will go into 72 nicely. 9 will go into 72 nicely. Don't believe 16 will. 25, 36. That's a large perfect square that will go in. So square root of, that's 36 times 2. Can break that apart. And that's going to be, square root of 36 is 6. And that's 6 square roots of 2. And that's as far as we can break that down. Okay, at this point, you may want to try one on your own. Even though there's a negative here, it's not going to affect it greatly. We're just going to basically tack that on at the end. Now, square root of 28, we can break that down into 2 and 14, 2 and 7. So this is the opposite of 2 times 7. There are 2 2's. We're going to pull one of those 2's out, and we get the opposite of 2 square roots of 7. Now, the largest perfect square I see in 28 is going to be 4. So it's going to be 4 times 7. Break that apart. We have negative 2 square roots of 7. Either way. Now, number 4, we have a variable. Now, do we treat that any differently? No, not really. We're just going to leave it alone. Now, the square root of 49, of course, would be 7 times 7 because it is a perfect square in and of itself. So I'm just going to go ahead and say the square root of 49 we can separate from the square root of x. The square root of 49 is 7, and we have the square root of x. So 7 square roots of x. 52, I'm going to break that down. 2 and 26, 2 and 13. So this is the square root of 2 times 13 times t. There's only one t. Now, the square root of 4 is going to be 2, or you see there's 2 inside, we pull 1 outside, times the square root of 13t. And that's as far as we can go. 13 is prime, and there's only one t. Okay, now, square root of 98x squared. 98, that'd be 2 and 49, 7 and 7. We have square root of 2 times 7 times x times x. And so we notice there are 2 7s, we can pull that out. There are 2 x's, I can pull that out. However, the square root of x squared is the absolute value of x. You cannot have a negative in the radicand. So it's going to be 7 times the absolute value of x times 2. So keep this in mind. This is important. The square root of x squared is the absolute value of x. So basically, you see 2 in, bring 1 out. Okay, now we see there are 1, 2, 3, 4, 5. You get the idea. So for each 2, I bring 1 out. So 1, 2, 3, 4, 5, 6. So we've got 6 x's there. Now, we do need to have to the 6th power. Here's where it gets interesting. When we pulled this out, that would be the absolute value of x. The thing is, even if we have a negative here, that's going to end up as a positive. So we could put the absolute value there, but if it's an even number that comes out, it's not really necessary. Number 8. Here we have m to the 26th power. Now, you hopefully have noticed by this point we're just taking half. Part of that would be because in actuality, taking the square root is actually raising something to 1/2 power. So 26 times 1/2 would be 13. And there's an odd number here, which leaves the possibility that if m were negative, that the result could be negative. Well, that can't be the case because m had to be positive because we're dealing with the square root function. So we need to have the absolute value of this. We need to ensure that whatever is inside there is positive, or the result would have been positive. Okay, here we have a little bit of a problem. We have an odd number. Now, square root of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of these. All right, now we've got 1, 2, 3, 4, 5, 6 of them. So we can basically, the trick is this. You say, all right, d to the 12th, so go 1 down times d. Now, d to the 12th, take half of those. So we've got 1, 2, 3, 4, 5, 6 of them, and then the square root of d. The question becomes, do we need absolute value here? If it's positive, if d is positive, then we'll yield a positive result. If it is negative, we'll still deal with a positive result because there's an even number of those negatives. So even though you could put absolute value, it isn't really necessary. So we're going to leave it in that form. So if there's an odd number coming out, we do need the absolute value. If it's an even number, we do not. Okay, 10. Square root of 250, y to the third. So we're just going to go ahead. It's 2 and 125, 5 and 25, 5 and 5. This is going to be the square root of 2 times 5 times 5 times 5, and then we have y squared times y. I'm going to go basically subtract 1, so y squared, and then have that extra that is there. Now we have a pair here. It's going to be 5. We've got a 2 and a 5 stuck inside. The y squared we can pull out, but we've got to make an absolute value because it's an odd number that's coming out. If it's an even number, we don't need that. So 5 times the square root of y. Inside we have just a 2 and a 5 and a y. And so we need to simplify that back down. So we have 5 times the absolute value of y, since that's an odd number, 1. And then the square root of 10y. All right. Number 11. Negative 2 onto the square root of 75. So negative 2 times, and now let's break that down. 75 is 3 times 25. 25 is 5 times 5. We have 3 times 5 times 5. 2 of them pull out, so we have negative 2 times 5 times the square root of 3. And we can simplify this. Negative 2 times 5 is negative 10. And there we have it. Number 12. We have 2x times the square root of 50, x to the fourth. A 50 we can break down. We have 2x times the square root of, let's see, that is 2 times 5 times 5. And then, of course, we have just that even number. We're going to take half of that and pull it out. And since it's an even number that's coming out, that will take care of the absolute value basically in and of itself. X squared will be 0 or positive. We have a pair of 5s, that will pull out. We're left with the 2 inside. So let's simplify this that has come on the outside here. 2 times 5 is 10. X squared times x to the first is going to be x to the third. And we have times the square root of 2. Alrighty. Now we're going to use some quotient properties here. And we need to be especially careful that we don't have a radical in the denominator. We'll have to rationalize it if it is not. So, number 13, we can split this up into the square root of 9 over the square root of 49, which would be 3/7. And so it's easy to work with. Again, 14, we can split this up, the opposite of the square root of 16 over the square root of 81. That is negative 4/9. Number 15. There's no obvious square root here, but we do have some perfect squares that we could pull out. So let's do 27. That'd be 3 times 9 and 3 times 3. So 3 times 3 times 3. 75. I can break up. That is 3 times 25, or 5 times 5. There's several things that I can do here. Number 1, I could actually split this up and since both of these are inside or they're in the radicand, under the radical, those actually will reduce because I could take that and make that the square root of 3 over 3, which is actually 1, and the square root of 1 is 1. So these will simplify out. Now the square root of, there's 2 inside, we'll pull 1 outside. 2 inside, pull 1 outside, and so we have 3/5. All right, the square root of 18 divided by 2. Now 18 we can split into 2 and 9, 3 and 3. So we have 2 times 3 times 3. And on the bottom we have the square root of 2. Now we're going to pull 2 of these, since we have 2 of these outside, pull 1, excuse me, we have 2 3's in the radicand, we'll pull 1 outside in front of the radical. So the 2 is left in the radicand, and we have square root of 2 on the bottom. Again, we can reduce this, since they're both in the radicand. Very important. If one's in the radicand and one is not in the radicand, it makes a much different situation, and we'll have to deal with that later. But in this case, they're both in the radicand. We can simplify those out, and we have just 3. Now, number 17, the square root of 12, we can break that apart into 2 and 6, 2 and 3. So the square root of 2 times 2 times 3. 75. Nope, I actually see it down here. 3 times 5 times 5. Now, 2's inside the radical, or under the radical, or in the radicand. That's going to pull 1 2 out. 2 5's, pull 1 out. And the square root of 3 divided by the square root of 3 is 1. So we're left with 2/5. Okay, number 18. 63. That is 7 times 9. 9 is 3 times 3. So the square root of, we have 3 times 3 times 7 times y squared times y. On the bottom, square root of 7 times y. Now again, we can pull one of these out, and we can pull 1y out, and that's an odd number, 1. So we need the absolute value. And then inside we have 7y. We also have 7y in the denominator. Now, square root of 7y divided by the square root of 7y is going to divide to give me 1. So we're just left with 3 times the absolute value of y. And again, the reason for the absolute value is to prevent having some kind of a negative in the radicand, which would give you no real solution. Again, we won't get to complex numbers until our next algebra unit, or excuse me, our next algebra class, Algebra 2. All right, we're going to rationalize the denominator. Why do we need to do this? Well, remember that a rational number is one that has no repetition, no bar notation, ever. Never stops. It is non-terminating. It is repeating. And so it must go on forever and ever. Well, that's one thing when you just have the number in and of itself, but it's another thing entirely to try to divide by such a number. It's just going to be impossible to do. So what we need to do is to make sure that we have none of these irrational numbers in the denominator. We're going to have to rationalize the denominator. We're not making the whole number into a rational number. We're just making sure that the denominator is a rational number. Okay. Wouldn't it be nice? It would be very nice if this number suddenly had 2 3's in the bottom. That way we could just pull, if we have 2 3's in the radicand, we could pull 1 out and we just have a 3. That's what we'd like to do. Now, to do that, I'd have to multiply by the square root of 3 here on the bottom. But really, I have to do on the bottom what I do on the top, so that really we have square root of 3 over square root of 3, which would divide to give me 1. But remember, we can always divide by 1, multiply by 1. 1 doesn't affect a thing. It's similar to if we took, say, a simple common fraction like 2/3, multiply by 2 over 2, gives me 4/6. We happen to know that 2/3 and 4/6 are just different versions of the same fraction. In the same way, this is going to give me a same fraction but a different version, one that's going to have a rational denominator. Now, the square root of 7 times the square root of 3 we can rewrite under one radical. And since we have two 3's in the bottom, we pull 1 out and we simplify the top, square root of 21. Now some students like to say, oh well, 21 divided by 3 is 7, we can reduce. Not so fast. The square root of 3 and 3 are much different numbers. In fact, the square root of 3 and 3, if you compared them using an inequality symbol, the square root of 3 is much less than 3. In fact, the square root of 3 is just less than the square root of 4, so somewhere around 1.7, 1.8, 1 and 7/10, 1 and 8/10. And so you can see that these are not the same number, so you cannot divide them out. If one's in the radical, or under the radical, and the radicand, and one is not, you cannot simplify those, so leave them alone. Square root of 2 over square root of 5. Now again, it would be very nice if I could have two 5's in the bottom instead of one, because I cannot leave this as an irrational number in the denominator. So what I'll do is I'm going to multiply by the square root of 5 on the denominator. But what I do to the denominator, I must also do to the numerator. Two 5's, pull 1 out, and we're left with the square root of 10 on top. Now again, it's very tempting. You see this square root of 10 is 2 times 5. It's very tempting to want to reduce these 5's. Don't do it. This is the square root of 5. This is 5. They're different numbers entirely. So we're done. Okay, the square root of 21. And there's some different things to be done here. We could simplify it and then rationalize the denominator, or we could rationalize it and then simplify it. Let me show you what I mean. I'll do it both ways. Now, let's first simplify. Square root of 9 is 3 times 3. Square root of 8 is 2 times 2, which is 4 times 2, which is 8. We have 2 inside, pull 1 outside. 2 inside, pull 1 outside. And we're left with the square root of 2 on the bottom. Now this simply won't do. We cannot have an irrational number in the denominator. So we're going to multiply the numerator and denominator by the square root of 2. That gives me 2 2's, pull 1 out. This 2 is already here. And we have 3 square roots of 2 on top. So that's 3 square roots of 2 divided by 4, and that is it. Now, since 1 2 is inside, 1 is outside, we can't reduce it. The other way to do it is to just simply rationalize the denominator first. Multiply by the square root of 8 over the square root of 8. That's going to give me the square root of 72 divided by the square root of 64. Again, there were 2 8's, so we can pull 1 out, or the square root of 64 is 8. We're left with the square root of 72 on top. That 72 would be 2 times 36, 2 times 18, 2 times 9, or 3 times 3. We have 1, 2, 3 2's, and 2 3's. Pull 1 2 out, pull 1 3 out, and 1 square root of 2 is left inside. So we have 6 square roots of 2 divided by 8. Now you may say, we got a different answer, so surely one method must be better than the other. The problem is this: 6 8's, these are both outside the radicand. They're not in the radicand, they're not under the radical. 6 8's is 3/4. We can reduce those because they're both not in the radicand. If you're getting confused, consider that. If you have, say, a friend you enjoyed doing things with, hanging out at their house. Now, picture this. One day, you and your friend hanging out, you're both outside doing your thing. Another time, you and your friend, you're inside, playing some games, hanging out, talking. But imagine if you have one friend that is outside knocking on the door. Hey, can I mess around, play, whatever? And you stay inside. No. And he stays outside the whole time while you're inside trying to get him to go away. That doesn't work. If you've got a friend and you're both playing outside, that works. If you've got a friend you're both playing inside, that works. If you've got a friend that's trying to play outside and you're inside trying to get rid of them, that is not going to work. So in this case right here, they're both inside. That's normal. These are both inside the house. That's normal. These, in this case, are both outside the house playing, if you will. That works. That's normal. What's not normal is to have one friend playing inside the house and one outside the house. That doesn't work. That just won't work. You can't reduce those. All right, so this reduces down. We're ready to go. Okay, square root of 5 over the square root of 12. Let's see. I'm going to go ahead and try to reduce this before I rationalize the denominator. It is less work, in my opinion. You don't have to. That's how I'm going to do it. So the square root of 5, oops, wrong pen. Square root of 5 over the square root of 12. So 12 is going to be 2 and 6, 2 and 3. So we have 2 times 3. And so 2 are inside, we'll pull 1 outside. And now we have to get rid of the square root of 3. So times the square root of 3 times the square root of 3. 2 inside, pull 1 outside. So that's 2 times 3 over square root of 15. 2 times 3 is 6. Now, one friend's playing inside the house, one friend's playing outside the house. That's not normal. You cannot work with those. If they were both inside the house, yes. If they were both outside the house, yes. But no, you cannot simplify that. Okay. In this case, we're going to break this apart first. We need to rationalize this denominator. So we're going to, it would be nice if we had 2 x's down here. So let's make 2 x's down here. What I do on the bottom, I must also do on the top. So we have square root of 3x over the square root of x squared. Keep in mind that this is going to be the absolute value of x. So this is the square root of 3x over the absolute value of x, because this is to the first power. And that's as simplified as I can get it. In this case, 24. I'm going to see if anything can simplify with the square root of 3 times 5 times x over the square root of 3 times, I'm going to go 1 down, remember, y squared, and have my other y. Now I'm going to sort of look. Now the 3's are both inside the house. Is that normal? Sure it is. You can both play inside. That works. So we're left with the 5x y squared times y. Now 2 of these can pull out. Since I'm going to pull out and get an odd numbered exponent here, I have to take the absolute value. And I have this 1y that's left here. Now, square root of y, I'm going to multiply by the square root of y. What I do on the denominator, I also have to do in the numerator. So I have the square root of 5xy divided by, now, square root of y times square root of y, that's going to be square root of y squared. The square root of y squared is the absolute value of y. I give the absolute value of y times the absolute value of y. Well, think about it. If this comes out, if y itself, not the absolute value, but if y itself were positive, positive times positive gives you positive. If it were negative, this could be negative times negative is negative. If it's 0, 0 times 0 is 0. So it really isn't necessary to include this absolute value because now we have y to the second, which is an even numbered exponent. And so we can remove that. If you wanted to put the absolute value, you're welcome to, but it's going to be the same result. Well, thank you so much for listening to Crazy Math Productions. Have a wonderful day.